So I'm going to derive the formula for the circumcircle and the incircle for a quadrilateral. So a quadrilateral has four sides, and so let's say A, B, C, D, and with the sides A, B, C, D, and so the question is the necessary and sufficient conditions for the radius of for to drawing two such circles, drawing each of these cases, circumcircle and incircle, and how to find the formulas for these radii in terms of A, B, C, D. I believe these formulas for the radii are due to Indian mathematicians, in fact, around 1500 or something, and from Kerala, in fact. This formula is and this uses trigonometry. So I think the Aryabhata and that gang came up with this, or even the school in Kerala came up with this sines, cosine, tangent, and that sort of, you do need that. I can't see how you can derive this simply using Pythagoras formula alone. But you can use just the Pythagoras formula to go a long way in triangle. So that's where we are going to start and then use those results here. So let's start with the general triangle. Let's say ABC are the nodes with the side lengths small a, small b, small c. So the lengths ABC completely describe a triangle. And if you look at the area of the triangle, it's the way I have drawn it. It's a half base multiplied by altitude. But altitude from here is, so if this is A, then this angle is A. So this angle is B, this angle is C, internal angle. A plus B plus C is, of course, 180. And the H is, you can see, C sine B. So this is half AC sine B. So AC sine B. So this formula, we can repeat it as AB sine C, and also have BC sine A. Now, at the time of, but the sine, Pythagoras and so on, the sine A cos A wasn't there. But we can eliminate that using simply ABC, as I'm going to show now. So if you look at X is also C cos B. I'll come to that in a second. But on the other hand, if using this angle, this is a vertical, so this angle is 90 degrees. So consequently, H squared is C squared minus S squared. So H squared is C squared minus X squared. But from this side, it's also B squared minus A minus X the whole squared, because this length is A minus X, if this length is X. So if you expand this, this is B squared minus A squared minus X squared plus 2AX. So X squared cancels, giving us the relation X equals A squared plus C squared, A squared plus B squared minus C squared. So I'm going to bring it to this side. So that's A squared plus C squared minus B squared over 2A. And consequently, X is that, and then we get H squared, which is C squared minus X squared. That is C squared minus this quantity squared. A squared plus C squared minus B squared over 2A the whole squared. So that, if I simplify in the next page, we get h squared is 2ac the whole squared minus a squared plus c squared minus b squared over the whole thing over 4a squared. So notice the numerator it's a difference of two squares, so that's a squared plus c squared plus 2ac minus b squared multiplied by this minus this. So that's 2ac minus a squared minus c squared plus b squared divided by 4a squared. But notice that this is a plus c the whole squared, and this is minus a minus c the whole squared. So we can write this as a plus c the whole squared minus b squared multiplied by b squared minus a minus c the whole squared over 4a squared. So again, if you use sum and difference, you get a plus b plus c multiplied by a minus b plus c, and here you get b plus c minus a, and b plus a minus c divided by 4a squared. But notice that this is the perimeter of the triangle. So if usually the semi perimeter a plus b plus c by 2 is denoted by s, so this is s. And then notice that s minus a is a plus b plus c minus 2a divided by 2. So that comes out to be b plus c minus a by 2, etc. b plus c minus, so this is s minus a, and so this is s minus b, this is s minus c. And we needed, there was a 4 here, so we just have to multiply by, because there's a 2 everywhere, 16, so the 4 cancels and you get a 4 here. And so h is going to be the square root of this, so that's going to be 2 over a multiplied by s multiplied by s minus a multiplied by s minus b multiplied by s minus c. So if I substitute this into this formula here, the first formula right here for h, half a cancels and you get the formula due to Heron for the area of the triangles, and this we will use. That's the reason I derived it, and also to show that you don't need any trigonometry for this. I believe this is somewhere long back, 60 AD or so, and when I am at this, I can also get the relation for sine A cos A in terms of the sides. So for that, we look at once again x was, we decided x was a squared plus c squared minus b squared over 2a. So I'm referring to this x. So we already have it here. X was a squared plus c squared minus b squared over 2a. But this is also equal to, if you look at the triangle, x is equal to c cos b. So if you cross multiply, you get the usual trigonometric identity. So you get a squared plus c squared minus b squared is 2ac cos b. Or we usually write b squared as a squared plus c squared minus 2ac cos b. So this gives us a similar relation is a squared is b squared plus c squared minus 2bc cos a. In other words, this angle refers to this side, etc. And so this is So we got the, well, if you want, we have the relation for cos A as A squared minus B squared plus C squared minus A squared over 2BC. Again, this will be a useful relation I can use. And in fact, we can use this sine A here. Sine A is sine squared A is 1 minus cos squared A. So that's going to be 1 minus B squared plus C squared minus A squared over 2BC squared. So again, the same trick that we did before, 2BC the whole squared minus B squared plus C squared minus A squared the whole squared over 2BC the whole squared. So the numerator will come out to be 4 multiplied by, if you go through the way we did this before. So we get the relation for sine A as square root of that. So 2 over BC multiplied by S multiplied by S minus A. All right, so area, which is half BC sine A also confirms that, of course, half BC sine A confirms that. But more importantly, you also get, so we have all this relation. So notice that all this has been, sine A we have in terms of, again, the sides ABC. Now, if you go back to a triangle in terms of the circles, suppose you draw the bisectors for each side, which is EC, A, B, C. So a bisector goes up, another bisector comes. These are bisectors, though this will be A by 2, A by 2. And this angle is 90. And so if you look at these triangles, these two triangles are congruent. We call it OB. Let's say this is D, OBD and OCD are congruent. Consequently, these lengths are equal because this length is common. This each side is A by 2, one angle is 90. And you can now, if you simply join here, and you can use the same, this is already perpendicular, so this angle is 90, and this is a bisector, so these two are congruent also. So this is also R. In other words, the well-known result that so a circumcircle is the intersection of the bisectors of each side, and they all meet, and that gives you this center. So the question is, what is, now we can use a circle property. If this angle is A, this angle is 2A, so each of this angle is A. This is 90 degrees, so this is 90 minus A. Notice that this is not a bisector of this angle. This is not. So this is 90 minus A, this is A. So from this figure, R over, or rather A by 2 over R is sine A. So this also gives us the identity that A over sine A equals 2R. And that, of course, expands as B over sine B and C over sine C. Another classic trigonometric identity. But the key is now we have, we can find the radius of the circumcircle. So that's going to be, so notice that sine A is here. So R is, so R is going to be A by 2 by sine A by 2 sine A. Sine A is this. So from here I get this is going to be ABC over 4 multiplied by as the area of the for the radius of the circumcircle for a triangle. Incircle is even easier because if you have if you on an incircle, the way you construct is you bisect the angles, and again you go through similar argument, and then wherever the you draw a perpendicular. So this is 90, and all the angles are equal, and one side is common. So these two triangles are congruent, and then you also argue. I'm sorry. You take these two triangles. These two by definition, these two are equal because we just bisected, and one side is common. So the two bisected, and so the two bisectors join somewhere. You drop a perpendiculars. So these are the radius. So this is A, B, C. So notice that. So you have to show that these two sides are equal. I guess. Yeah, it goes the same way. So you drop perpendicular. So these angles are 90. This angle is this angle is 90. These angles are equal. So these two angles are equal, and you have this side, and you have so you have one side and two angles equal, because this angle and these two angles are equal. These two angles are equal because actually all the three angles are equal. So these two are congruent, and similarly you can show this. So all these three distances are the same r. Now small r is easy to compute because the area of this triangle is r multiple. So area of this triangle is small r a multiplied by ar by 2. So similarly br by 2 and cr by 2. So total area is half multiplied by a plus b plus c by multiplied by r. But this is s, so that's sr. So small r is a over s, and the a is of course square root of s minus a. And so that's the formula for the incircle of a triangle. But now we want to use all this to compute this. So I guess all this goes back to around that time. So let me come to a quadrilateral, and we'll use some of these results. That's the only reason I. So a quadrilateral has four sides, A, B, C, D. So A has angle A, B. So this side is A, B, C, D. So first it is, so let me find the area of a general quad. So you can see natural way is to bring in what we learned. So call the diagonals. I'm going to call this P. The other diagonal is Q. And there is a relation between P and Q from Ptolemy. I'll just state it when I need it at that time. So notice that the area of the quadrilateral area is this area of the two triangles. So that's going to be half AD. Let me half AD. Well, let me call this triangle. This let me call this between A and C to be use this diagonal. Let me start all over again. So a general quadrilateral question is what is the area, then we will go to the so I'm going to draw this side to be A, B, C, D. This angle is A. So this angle is C, B, D, etc. So the total area is area of this triangle plus area of this triangle. So from what we did earlier, notice that it is area of a triangle is BC, a BC and the included angle, BC and included angle sine A. So this is going to be AB and half AB sine A included angle plus half here CD sine C. And or I'm just going to call it 2A. So 2A is AB sine A plus CD sine C. So to simplify this, I want to simplify it as much as possible. And so I'm going to square it. So I get to 4A squared is AB sine A plus CD sine C, the whole squared. So that's going to be several terms, A squared, B squared, sine squared, A plus C squared, D squared, sine squared, C plus half ABCD sine A sine C. So from the figure we can also use the quadrilateral relations. So we get p squared. If you take this triangle, the p squared can be written as a squared plus b squared minus 2ab cos a, which is also from here c squared plus d squared minus 2cd cos c. So let me bring in the square terms and the cos terms to each side. So you get a squared plus b squared minus c squared minus d squared is 2ab cos a minus cd cos c. So I'm going to square this so that this becomes a squared plus b squared minus c squared minus d squared, the whole squared, over 4 is a squared b squared cos squared a plus c squared d squared cos squared c minus 2abcd cos a cos c. So I want to combine this with this expression for a squared. So notice that you can begin to see that. So if I add both these terms, 4a squared plus you have to have some faith in this now. A squared plus b squared minus c squared minus d squared over 4 is we are going to add this term to this, so that gives us a squared b squared plus this term, that's simply c squared d squared. Then you have so this should be 2, not half. 2 ABCD sine A sine C here minus cos A cos C. So that's going to be cos A plus C, because cos A cos C minus sine A sine C is cos A plus B with a minus sign. So that's 2 ABCD cos A plus B, cos A plus C. And now I'm going to bring this term to the other side. And so I have to multiply by a 4 throughout. So this becomes 16a squared plus b squared. So notice that there was a square here, or minus c squared minus b squared. So it's a little bit doing equals. This 4 goes here, so this becomes so if you want, we can rewrite this as AB plus CD the whole squared, and do a little bit simplification here. So let me do that before I come in here. So this is the same as AB plus CD the whole squared. So that's going to be a squared b squared plus c squared d squared minus 2abcd. Here you have this. So if you combine with all that, this will become so I should add minus 2abcd. Then you have minus 2abcd cos a plus c. So this can be further simplified because this becomes ab plus cd the whole square minus 2abcd. If you pull out, it becomes and if I pull cos 2a as 2 cos squared a minus 1, this becomes 4 abcd cos squared a plus c by 2. So that's the formula I'm going to plug it in here. So this multiplied by so this is equal to, I'm going to multiply this 4 here, so that becomes 2ab plus cd the whole square minus 16 abcd cos squared a plus c by 2. The question is how far we can simplify this side. So let me make sure that this is, so this side goes to the other side. So this will have a minus sign here and then plus this. So this term plus this term. So I'm going to rewrite in the next place clearly. So 16a squared is 2 multiplied by ab plus cd the whole squared minus a squared plus b squared minus c squared minus d squared. And then the minus 16 abcd so minus 16 abcd this term. So I'm just going to leave it on this side. So that will be plus 16 abcd, so that I can add it at the end, cos squared a plus c by 2. Let me just simplify the right side. So this squared here. So again, notice that this is a squared minus b squared. So we can apply that twice. So you can see this is going to be a squared plus b squared minus c squared minus d squared plus 2ab plus 2cd. That's one term multiplied by 2ab plus 2cd minus a squared minus b squared plus c squared plus d squared. So if I combine a squared, b squared and 2ab, so you get a plus b the whole squared. Here minus c plus d the whole squared. C minus d the whole squared. Multiplied by c plus d the whole squared minus a minus b the whole squared. So again, if you do this up and down, you get a plus b plus c minus d, a plus b plus d minus c. Here you have a plus c plus d minus b, and one more term, b plus c plus d minus a. And so this is, if I call S to be a plus b plus c plus d by 2, the semi-perimeter, then S minus a, notice that is a plus b plus c plus d minus 2a by 2. So that comes out to be b plus c plus d minus a by 2, this term. So this is S minus b, this is S minus c, and this is S minus d. So we get 16a squared is S minus a multiplied by S minus b multiplied by S minus c multiplied by S minus d, and I'm going to keep tab of that ABCD term. All right, so this seems to be the formula for a general quadrilateral, and so I don't know how far this goes. So maybe to the Indians, I'm not sure. In any case, let's come to the problem of circumscribing a quadrilateral. Not all quadrilaterals, as you're going to see, there's a condition. So suppose you can do it. Then you have, of course, a center, and all these are the radius of the quadrilateral. Then notice that if this angle is A, B, C, D, then this angle is 2A because this is the center. That's a circular property. So the angle extended at the center is twice the angle at the. And similarly, if this angle is C, this is 2C. So you can see 2A plus 2C is 360, or opposite angles or add up to 180 degrees. So I guess I see that there's a note here saying that's due to an Brahmagupta. So an Indian astronomer, I don't know, probably 11th century or something, I'm just wildly guessing, right? Aryabhata Brahmagupta, so that's cool, I think. And there's a question is now, what is the radius of that? How do you find the radius? So if you recall, in the triangle, we had a formula that we can use. So this is for this is Ptolemy's time or whatever, Greek's time. So here, if you, first of all, I made a slight mistake here. So in this formula, there should be, because of this 2 and there are 4 factors, so there will be a 16 here. So basically, a 16 cancels off and you get the a squared. The area of the quadrilateral is s minus b multiplied by s minus c multiplied by s minus d minus abcd cos squared a plus c by 2. Okay, so that's the general area of a quadrilateral. And if you can circumscribe if you can draw a circle outside the quadrilateral, then a plus c is pi, or it's a cyclic. They call it cyclic quadrilateral. So the opposite sides add up to 180. So this is true for b plus d also. So that's the necessary and sufficient condition to draw a quadrilateral, and to draw a circle through outside the touching all the 4 corners. And since a plus c is the area simply turns, so remember this is a square, so area turns out to be s minus a multiplied by s minus b multiplied by s minus c multiplied by s minus d, everything in terms of this side. That's because a plus c is by 2 is 90 degrees, cos 90 is 0, so this term is 1. So that's the area of a cyclic quadrilateral. And the cyclic is property is this. A plus c is or b plus d is also pi, of course. And now we can use a trick. So if I call this to be p, one diagonal, and the other one is q, but let me concentrate on p. Then notice that this quadrilateral, this circle has to go through it goes through this circle, the triangle ABD, and also triangle BCD. And it's the same circle with the radius r. So we can use an earlier formula, which we had here. The radius is ABC over P, A equal to ABC over 4R. So we can use this formula to get this. So this is a good trick. So area of the triangle A1 is, let's say, A, B, C, D. And then it is AB, and let's say that this side is P. So this is ABP over 4R. And similarly, A2 is CDP, PCD over 4R, the same radius, but A1 plus A2 is the total area. So you get area is AB plus CD over 4R multiplied by P. So only thing is we need to know what is P. So we can use a result by Ptolemy. I'm not going to derive it. You can find it for P and Q. If this is P and this length is Q, so it's getting messy, so I'm going to draw another quadrilateral. So this is P and this is Q. Then Ptolemy's relation is P over Q is EAD plus BC over AB plus CD. And the AC PQ is AC plus BD. So this is actually the Ptolemy's relation. And if you if you use this, then P would turn out to be using those two relations, AD plus BC multiplied by AC plus BD over AB plus CD. And all we have to do is substitute this into this formula and we are done. And that, I guess, is Parameshvara's result. So we get area, which is AB plus CD, AB plus CD multiplied by P over 4R. And the P is here. And so notice that AB plus CD, one factor cancels off because it's in the square root. So this turns out to be AB plus CD, three factors, AD, AC plus BD, all the three terms you can generate, AD plus BC divided by 4. And the area, of course, we have here in terms of the sides. And the area also has a square root. So the radius turns out to be this divided by 4a. That's 1/4 of AB plus CD multiplied by AC plus BD, AD plus BC over S minus A multiplied by S minus B, S minus C over S minus D. And this is Parameshvara's formula. Actually, his I don't remember exactly, but 1400 or 1500 somewhere from the southern part of India, Kerala. His actual name, whole name is Parameshwaran Namboothiri. So Namboothiri's are sort of scholars at that time. So anyway, there were a couple of mathematics schools, and I think the trigonometrical series, expansion of the Taylor series, etc., were done there around this time, 1400, 1500, or 1300 or something. The Taylor series expansion for sine x, tan x, etc. Encircle is even easier because you can see if an encircle is possible. So you have a quadrilateral, and if an encircle is then these are tangents, and you can see that this is 90 degrees, and this is so if you take these two triangles, they are congruent because you have 90 degree here. This is the radius, and this is the radius. And this side is, of course, common. And consequently, if this is alpha, this is alpha. Similarly, if this is beta, this is beta. And then if this is gamma, gamma, delta, delta. So you can see this is alpha plus beta plus gamma plus delta. Alpha plus beta, gamma plus delta. So what I'm trying to say is if this side is A, B, C, D, if you have an encircle, the condition seems to be that the opposite sides add up equal. A plus C is B plus D. This is actually necessary and sufficient. I just showed it is necessary. You can actually argue a little more argument. You can show that it's also sufficient. And then the area is easy because if this is R, And the area of this triangle is simply small r multiplied by, let's say, a side half AC. So that's, you do it on all the four sides. So area of the quadrilateral will turn out to be half A plus B plus C plus D multiplied by small r. And this is SR. So R is A over S. So this will turn out to be S minus A multiplied by S minus B multiplied by S minus C multiplied by S minus D. And minus, we had gone through this before, ABCD cos squared A plus C by 2. Remember, this is a general quadrilateral. So in circle, this angle doesn't need to be 180. And square root of this divided by 1 over S. So that seems to be the inside radius. So we have everything now. The necessary and sufficient condition for a incircle is that the opposite sides add up sums are equal or add up equal. And then, as I said, if you these two triangles will be congruent because we have two sides are common and the one angle is 90 degrees. And so here we have derived the incircle radius and outcircle. And in particular, of course, if you can do both incircle and outer circle, then the A plus C is 180 and the formula reduces to, for the radius, even simpler.